Welcome back to 8701. In the previous lecture, we have seen how the gauge bosons, the W and the Z boson, acquire mass, while the photon remains massless through the Higgs mechanism. We introduced a new field, a new complex duplet scalar field, the Higgs field, which then broke through its vacuum expectation value, the symmetry, and then through the coupling to the gauge bosons, they acquired mass. Great. But we also have to find a solution for the fermions. We cannot simply add a fermion mass term to the Lagrangian. That would change, or that would break the gauge invariance. So how do we do this? We do this in a very similar way, even easier. But before we look into how this is done, let's have a look at the masses itself. It's spectacular. The top quark is our heaviest known fermion, has a mass of about 172 GeV. The tau has a mass of 1.77 GeV. The muon is an order of magnitude lighter with 0.1 GeV. And for the electron, we have to go to 0.51 MeV. Okay? And we haven't even tried to understand, or we are not able to measure actually the masses of neutrinos. We will talk about neutrinos in one of the following lectures. So here you have 6 orders of magnitude, and you have to go further down here in order to find the neutrinos on this mass scale. So we have to have a mass-giving mechanism which allows, this broad spectrum of masses to occur. And the very simple ad hoc mechanism which was introduced to the standard model is one where the particle simply interacts with the Higgs field. So we have our Higgs field here. We have let's say we have a left-handed particle coming in, and the interaction with the Higgs field turns it into a right-handed particle. This is a little bit simplified, but what we do here is simply introducing terms into the Lagrangian which do nothing else. We turn our left-handed particles via the interaction with the Higgs field into right-handed and the other way around. And we have to do this for up-type particles and for down-type particles. So here is another view at this. The strength here is the mass of the particle over the vacuum expectation value. This number here, this lambda d, is the so-called Yukawa coupling. And those Yukawa couplings now change from fermion to fermion. Each fermion comes with their own Yukawa coupling. It's basically a free parameter in our theory in the standard model. So instead of talking about the masses being free parameters, we talk about the coupling to the Higgs field as free parameter, but they are one and the same. All right, so this was rather straightforward. It's a simple coupling. You introduce this term ad hoc and then hope for the best that it's actually realized in nature. And we'll see that this is indeed the case for some of the fermions later.